Welcome back, everyone. So today we are going to start the Chapter 8 lecture note outline. So you'll want to get a hold of that before you follow along with the video. So we're going to be working through the first part of Chapter 8 today. And in Chapter 8, we are going to extend our knowledge about how the atom is actually structured. And we're going to be focusing our attention on the part of the atom that we're really interested in chemistry, which is the electron. So up until now, we've really kept our vision of the electron pretty simple. And we know it's a negatively charged particle, and we know that the atom has a nucleus in it that balances that charge with a positive charge. And we've learned about the different elements and how they're different from one another. And now we're going to take things a step further. We're going to look at what's called the modern atomic theory. So modern atomic theory, that's what Chapter 8 is all about. And the reason why we're learning the modern atomic theory is that it will give us the ability to understand why some of the things that we have seen so far, like the charges of different nonmetals and metals being what they are, so it will give us some insight into why that happens and how it works. It will also give us a lot more power to understand how compounds actually form. It will give us insight into why we have what is different from salts or ionic compounds and molecular compounds, and why that might be the case. It will also give us the ability, more importantly, or at least as importantly, to be able to, rather than just draw chemical formulas, but actually be able to draw structural formulas and predict some of the properties based on those structural formulas for different compounds. So it extends our abilities quite a bit. And so that's why we're covering this here in Chapter 8. We're going to get this sort of foundation that take us forward into the next unit and the rest of the class by understanding this modern atomic theory. So here's some basic information about it in this box. Basically, around the early 1900s, late 1800s, people started to really get a handle on electricity. So we discovered electricity, and then kind of coincidentally we started studying the properties of light and how light interacts with electricity and matter all at the same time. And different people observed a lot of interesting phenomena that had them sort of question a lot of the sort of assumptions they had made previous, and also ask a lot of new questions. So that's what we're going to be learning about is we're going to sort of take it kind of the way that the scientists took it, and see how actually it turns out light can give us some really deep insight into actually the structure of the atom, more than just the simple view of where there's a nucleus in the middle and there's this electron on the outside. It's going to give us a lot more information. So to do this, the first thing we're gonna look at actually is light, because in order for us to understand what's going on here, we need to understand, first of all, how we can think about light, and so we have some words to use and some sort of understanding about what's going on with light, at least from a basic perspective. So what we're going to talk about is at first are the properties of light. And we're gonna keep it simple, but just enough information for us to sort of understand this stuff. First off, what exactly is light? Well, our current understanding of light is very sophisticated, but what we know is that essentially, if you have a charged particle like an electron or a proton or any other charged particle, and you accelerate it through or oscillate it through an electromagnetic field. Now that's a field of a magnetic field, which we're going to call the electromagnetic field. It will actually emit, when it oscillates through this field, a little bit of energy. And we call these little bits of energy photons, which are the components or the subatomic particles of light. It's a little bit of energy. And this stuff, these photons, have very different properties than what we're used to seeing with other particles, like at least right now, which we're actually going to see later on, that all of these particles have this strange behavior in common with one another. But photons are a little bit different than the other particles that we have, right? We know that, for instance, a proton has a mass and an electron has a mass. And usually we're used to dealing with things, at least around us, most of the time, that have a mass. Like if they exist, they weigh something. Well, photons actually are not like that. Photons, interestingly enough, have no mass. They are massless particles. And actually, they belong to a class of subatomic particles that are massless. They have no mass, which does actually help explain some of the other properties of photons. Most importantly, their velocity. So actually, photons, they have quite a bit of energy packed into that little photon, that particle. And when they are traveling, we observe them, at least in a vacuum, traveling at a speed that is quite extraordinary. It is actually 3.0 times 10 to the 8th meters per second. And that is called the speed of light. And it turns out that the speed of light is a sort of maximum velocity that anything can attain in a vacuum that we know of. So this is sort of the maximum speed that anything can go, and photons have it. Okay, so that's some of the basic stuff, just informative about light. They're massless. Light has no mass, but it does have a velocity. Now, another thing about light that is interesting is that it has very obviously a wave nature to it. It behaves like a wave. And what I mean by behaving like a wave is if we sort of divide up what we know about things around us into some sort of different properties, we see that there are things that act like particles and things that act like waves. Now, things that act like particles would be, like a baseball or a ping pong ball, or really any object that has a discrete location in space. Okay? Particles have a discrete location in space, and they're concentrated right there. Now, waves are not like that. Waves are spread out in space, and this gives waves some very different properties than particles. So, for instance, if you throw a baseball through the air, it hits at a specific location, one place. You can catch that one baseball. But waves do interesting things, like they don't hit exactly at one space. They are spread out. Like if you watch a wave at a beach, it will hit at many places on that beach, as it'll hit heavier in some places and lighter in others. Light and waves do other things as well, like they diffract around corners. Baseballs don't do this. So let's talk about waves a little bit to get some more information about them. So one of the first things to note about waves is they have something called the wavelength. Okay, the wavelength for a wave. What is the wavelength? Well, the wavelength is, when we're describing a wave, we have to take into a consideration that it has these different things that we call peaks. Okay, so we have a peak over here, and this is called a trough, or the minimum point, and the peak is sort of the maximum point, and we have another peak over here. So let's call this peak 1, we'll call this peak 2, and this is like trough 1. Now what the wavelength is the difference between successive peaks or successive troughs. So if we locate the main point of this, the maximum peak here for this part of the wave, and this one, and then we measure the distance between these two successive peaks, this is called the wavelength. This is called the wavelength. And we give it a symbol. The wavelength gets a symbol that looks like this. And this is called the Greek lambda. The Greek letter lambda. And that is the symbol that we give to the wavelength for any wave. Right? This could be a wave of light, a wave of sound, or a wave in the ocean. Okay, any wave that we are considering does have a wavelength that can be measured and established. Okay, and we're going to define it right here. I'm going to just write down some notes about it. So the wavelength lambda is the distance between successive, meaning after one after another, peaks. And I'll write down here, or troughs in a wave. Okay, so that's the wavelength. Now, different waves will obviously have different wavelengths, and the wavelength is a primary characteristic of a wave. So you'll see that light, for instance, the light that we see, visible light, has wavelengths that are very small, but they're not nearly the smallest wavelengths that you can observe in the electromagnetic spectrum. They're on the order of 400 nanometers in distance, separating different peaks. Now, if you go to the ocean, obviously, and you watch some waves on the shore, they're much farther apart than 400 nanometers. They might be 40 meters apart. So the wavelength definitely changes the properties of a wave. And we were going to talk about that specifically with light, how the different wavelengths affect the properties of different forms of light. So let's talk about another property, which is called the amplitude. The amplitude of a wave is represented here. So this is the amplitude A. The amplitude A is the height from the baseline, and the baseline is this middle point here. From the baseline to the peak of the wave. Okay, so what is the baseline? Well, the baseline is the line that cuts through the middle of the wave peaks, such that you have sort of the amplitude that is here, which is positive amplitude, is the same as the negative amplitude over here. And this sign that I have here, either positive is above the baseline or negative below the baseline, that is called the phase, which is positive or negative compared to the baseline. Okay, so if you're above the baseline, positive amplitude. If you're below the baseline, it's a negative amplitude. Now let's talk about one more property of waves, and that is the frequency of a wave. The frequency of a wave, we occasionally used a few different symbols for this. Commonly, though, when we're talking about in chemistry, we use the symbol which has the Greek letter nu. So this is the Greek nu. Occasionally, we will also use the symbol F, which is also used for frequency. So these are both used commonly to describe something known as the frequency. Now, what is the frequency? Well, the frequency is essentially the rate. I'm going to change colors here. It's the rate at which a wave peak passes through a fixed point on the baseline. Okay, so if we picked a fixed point on this baseline, which I'm going to use a green here for, say right here. Now this wave is stationary. It's not moving forward or backwards. Now most waves, like you can imagine a water wave moving forward or a sound wave, they propagate in a particular direction. So you'll see the wave actually propagate, say forward or backwards. And as it propagates or oscillates through, you can actually measure the frequency by measuring how often each peak of the wave, one of those peaks of the wave, passes through that point on the baseline. and can't make a count. And this is referred to as the frequency. And it's usually given in units that are derived from seconds. And specifically, it's how many times per second. So very, very commonly we say it's how many times per second. And this gives us the unit of the hertz, which is how many times per second. Okay, so if we had something that was, say, like 125 hertz, that is equivalent to saying it's 125 times per second, okay, at a rate of 125 times per second. That wave is passing through a point, okay, and that's called the frequency. And we give the symbol nu, or F, to that. So now that we understand the basic language describing waves and what it means, we can talk about the type of wave we're really interested in at the moment here in chemistry, which is actually light. So we're going to talk about light, mostly because of the way that light interacts with matter is very interesting to us, and it tells us a lot about the nature of the atom. Now, to understand what's going on when we're going to look at soon how light interacts with matter and why that tells us certain things and how we know those things, we're going to need to really understand the energy that the changes in energy that are going on. So to get at that, we're going to need to talk about the energy of light. Now, you might remember if you go back kind of the beginning of the course, we talked about the difference between kinetic energy and potential energy. Okay, and I made a little diagram where, there was we had this sort of hill, and there was a boulder up top, right? And the boulder, based on its position, high versus low, represented two different potential energies. Okay, now when that boulder sort of rolls down the hill, we're converting the potential energy, which is based on its position, into kinetic energy, which is based on its movement. Kinetic energy, again, is based on movement. And potential energy is stored energy based on position in a field or some other means. Okay, so Ke is kinetic energy, that's movement energy. And potential energy is stored energy. Okay, so that's kind of the first basic thing. Now, what about light? What is light energy? Is that potential energy or is that kinetic energy? Well, we're talking about these waves moving through space, right? And because they're moving, right, based on this particle, oscillating through a magnetic field or whatever, that's all totally talking about movement. So that's what the energy of light is, first of all. It's kinetic energy. It's a form of kinetic energy. All right, so let's try to write it down and try to get at what it is and how it changes. What has more energy in it, this light or that light? That's what we want to be able to say. Well, it turns out this relationship is known. The relationship between energy and the wave of light is defined as follows. It turns out the energy of light is inversely proportional to the wavelength of light. Okay, so I just threw a couple of things at you that you haven't seen before. This symbol here, for one. This little symbol here, which is, if I drew it a little more carefully, it would look kind of like a partial infinity symbol. So it's like an infinity symbol with part of it cut off. What that symbol is the proportionality symbol. And a proportionality is if we see the thing on the left, how that changes with respect to the thing on the right. Okay, so that we're going to use that proportionality symbol a lot to see if we change one thing, how the other thing changes. It's a nice little convenient tool when we don't know exactly how the two things are related, but we want to figure it out. We usually start by thinking about how they are correlated in terms of their proportionality. Okay, so this is the proportionality symbol. Now let's try to understand this proportionality that I've shown here between energy and its wavelength. And I'm going to write it down, sort of translate it into English first. What this is saying is that the energy of light is inversely proportional to its wavelength. Inversely proportional. So what does that mean exactly? Well, if you look at the actual kind of equation here, and you think about what happens to E as the wavelength is changed, you'll start to see that they're related. One travels in an up direction as the other travels in a down direction. So for instance, if I put a large number for the wavelength, so the wavelength has increased, what happens is we divide 1 by a large number, and that gives us to get E, which gives us a small number for E. Conversely, if I decrease the wavelength, the energy goes up. So if I increase the wavelength, the energy goes down, and if I decrease the wavelength, the energy goes up. This is known as the inverse relationship between the energy of light and its wavelength. Okay, whenever we have this, one goes up, the other goes down relationship, that's called an inverse proportionality or an inverse relationship. So that's a really important point that we're going to carry forward and use this information when we start looking at energy changes when light interacts with matter. We're going to remember that we have this inverse proportionality between the energy of light and its wavelength. If one goes up, the other goes down, and if the other goes down, the other goes up. Okay, so we're gonna continue with this on the next page. Keep in mind, though, that we also, besides wavelength, we also have this parameter frequency, which can also be related to the energy of light. But I want to look at the next page before we talk about that. So let's go to the next page, and I want to show you some information about, some graphical information about the electromagnetic spectrum, which really helps us understand what's going on with light and what different forms can it take beyond just the visible spectrum that we see. So let's go to the next page. So here we are in the next page of the electronote outline, and we're going to talk a little more about the electromagnetic spectrum. So I'm going to show you some sort of images here to help connect kind of the theory to something you can see. Now, what we call visible light is a part of what we call the electromagnetic spectrum. It's what we can see with our eyes. And actually, the wavelengths, I should say, are give us the light that we can see with our eyes. And this visible spectrum has wavelengths, as I was mentioning before, that are around 400 nanometers. Now, if you stretch those wavelengths out, you get into a different part of the electromagnetic spectrum. So if you have longer wavelengths than visible, we go into a part first called the infrared. And then if we make them even longer, we get into the microwave region, and then we would get into the radio spectrum. Now, to give you an idea of the wavelengths in the radio spectrum, they're much, much larger than the wavelengths of visible light. So radio waves, for example, are around 10 to the 3 meter. So this would be like the size between a very large skyscraper and some mountains. So if you look at a radio wave, compare it to the size of, say, a mountain, it would be comparable in its size, the width of a mountain, or the distance between skyscrapers. That's radio waves. And then if we sort of shrink them down to microwaves, which you use in your microwave, these are somewhere between like a butterfly and a human being, the size of the wavelengths. And then we get down to visible, which are the wavelengths for visible light are subcellular. So these are like very simple single-celled organisms, the wavelengths for visible light. Obviously, I can't draw them to scale here because we wouldn't see them. And then we can also decrease it even further beyond visible. And when we do that, first we get into the ultraviolet region, which has significantly smaller wavelengths, and these are around the size of molecules. So look, if we look down here at this part of the graph, you'll actually see the visible spectrum. We have red up at this end, which has longer wavelengths than yellow and green and blue. As we go from here at red down to blue, we are lowering or making smaller the wavelength. We have smaller and smaller wavelengths as we go from left to right. Okay, and then we get into the far end of this low end of the visible spectrum. We get into purples, and then we get into the ultraviolet. Ultraviolet is beyond our visible range, but it has very short wavelengths. And as you saw earlier on the previous page, we know that the energy of light is inversely proportional to its wavelength. So if we have very small wavelengths, right, we have down here very small wavelengths, we have very high energies. So the energy that we see on this end by ultraviolet and lower, this is very high energy. Over here at radio waves, we have very low energy. Okay, and if we go between them, we have many, many energies possible between this high end and this low end. So longer wavelengths, lower energy, like radio waves. Smaller wavelengths, we have higher energies. So if we go beyond ultraviolet, and notice here is kind of interesting, like, you know, if you get exposed to too much ultraviolet radiation, that's high energy, you can get a pretty bad sunburns, right? However, if you're exposed to too many radio waves, nothing happens. They actually just pass right through you. And many times they just go over you or under you anyway, because they're much larger than you are. If you go beyond in the ultraviolet and smaller wavelengths, we get into things that are much more damaging to humans. The X-rays, which are very small. These waves, the electromagnetic spectrum in this area, have wavelengths that are around the size of an atom, so 10 to the negative 10 meters. We can even go beyond that, actually, and the smallest waves possible are actually in the gamma ray region. These are waves that have extraordinarily small wavelengths, the size of atomic nuclei and subatomic particles. So 10 to the negative 12 meter. These are extremely high energy and very, very dangerous to be exposed to. So high energy, low energy, short wavelength, long wavelength. That's kind of the main idea here. Now, another thing to think about, though, is like what's going on with the frequency of these things. So if I were to ask you, like down here at the gamma ray region, is that a low frequency or a high frequency? Or at the radio wave, is that low frequency compared to gamma rays or high frequency? So it's actually interesting to talk about that for a second. If you think about it, when you have a short wavelength, you have to have a higher frequency. So this over here is low. Oh, that's not working out well. Let me change how I'm doing that. Down here is low wavelength, but it is a high frequency. Okay, down in this region. But if we go up here, we have a high wavelength, but a low frequency. Let's use the symbol nu for frequency. So that tells us something about the relationship between energy of light and frequency. Those are directly proportional to each other. So let's write that down real quick. The energy of light is directly proportional to its frequency. However, it is inversely proportional to its wavelength. So there's a direct relationship with frequency and an inverse one with wavelength, okay? So that's an important thing to note also. And before we move on to the next part, I just want to talk a few more seconds about the visible light. Notice that down in the more red part of the spectrum, where we have a longer wavelengths, that red is lower in energy than, say, violet or blues, which are towards the shorter wavelength or higher energy part of the spectrum. So if we are comparing the energy of light, we can figure out its relative energy level. And if we're talking about visible light, it's pretty easy, because we know like red is down here at the lower energy, longer wavelengths, and violet is up here at higher. So if we're going in this direction, it's higher in energy, and if we're going in this direction, it's lower in energy. Now, as I was mentioning before, light with its wave-like properties has things behaviors it does or phenomena it exhibits that are a little bit foreign to us if we're used to dealing with a lot of particles like we are. For instance, if you pass light through a prism, a material that diffracts it, that material, what it does is the different wavelengths of light that go in end up bending through the material in different ways, through different paths through the material. So if you have, say, white light that comes from like an incandescent light bulb, it travels until it reaches some material, and then based on the material properties, different paths will exist depending on the wavelength. And this gives us what we can call as a diffraction pattern on the other side. So if you put a screen up or something to see this stuff, you will see what we call a spectrum. And that spectrum, we're going to be looking at spectrum, or spectra for plural for spectrum, for what happens when light originates from different types of matter, and what kinds of spectra do we see. And we can look at the different colors to get an idea of the energies involved. So we see here some purple. This is the higher energy, because we know that is a shorter wavelength, right? And we see over here red, which is lower energy, right? Because it has a greater wavelength, okay? So we can actually look at the light and look at the energies that are present in the light once we've sent them through a prism and then separated them. So a prism is kind of like a tool that we can use to separate a light, which is a mixture of different wavelengths, into individual wavelengths, and then do some analysis on that to understand what's going on. So this is the dispersion of light through a prism. Now we're going to go into the next page, but before we do that, I'm going to go to another screen because I want to show you some visuals of some experiments that I usually do in the classroom, but we're going to do here in the video in a more of a static way, so I can show you the way that light interacts with matter, different kinds of matter, and what we get when we pass that light through a prism. So let's go take a look at that. So I have a few pictures here. The first picture I have up top left here is of just a regular incandescent light bulb, and we're just looking at it without any kind of a prism in front of it when the picture was taken. So regular incandescent bulb with no prism, and then down here on the bottom right I have the same bulb but with a prism in front for the camera. And what's going on here is that the white light is entering through the prism, and the prism is separating that light into the different components that are present in that beam of light. And we see a rainbow pattern through the prism. We see the typical like red, orange, yellow, green, blue, and purple or violet. And then, so that's what we're seeing with that through the prism. So we see that this light coming out of the incandescent light bulb has all of the different wavelengths of the visible spectrum that we're familiar with. Notice, I want you to pay particular attention to the fact that it's continuous, meaning there are no, all the colors are there, and there are no gaps in between the colors. This is what we call a continuous spectrum. And we're going to go into defining these terms on the next page. But just for now, note that that's called a continuous spectrum. Now, what's going on here with this light bulb, and how is it all working? Well, typical light bulb, this is an incandescent light bulb. And incandescent light bulbs, though they're not as popular anymore, I still really like them a lot. They're not as efficient for a lot of reasons, but they produce a nice light. Anyhow, we have in a light bulb sort of this glass container which contains the apparatus that makes it light up. Essentially what you've got inside of here is a gas. So the light bulb was evacuated and then pressurized with a gas that does not react. It doesn't have oxygen in it. So there are a lot of different gases that can be used for this, but things like halogens are often used. In incandescent bulbs, it might be nitrogen that's in there as well. Anyhow, there's some inert gas that doesn't react. It's not oxygen. That's the important thing. You've also got really important part of incandescent bulbs is this little coil here. That's called the tungsten filament. It's an element tungsten. And tungsten is used because it has a very high melting point, meaning it will not liquefy or turn into a liquid from a solid at very high temperatures. It takes many, it's like, I think it's a few thousand degrees Celsius before tungsten will start melting. And it never reaches that temperature in typical circuits that we use in the house. And those are supported, and there's all this other stuff. But basically what goes on here is that there's energy is supplied in the form of an electrical current. So you've got the electrons traveling through, they go through the coil, and they heat it up. And the reason why is that coil is resistive to the flow of electrons. So when the electrons hit the coil, it's kind of like water that's traveling through you've got this high pressure water going, say, through a giant pipe, but then you force it to go through a very small hose. You get a lot of pressure going through it, and you can even burst the hose depending on the pressure of that water that's coming through. It's kind of like that a little bit, just an analogy. But as the electrons travel through this coil, they heat it up because there's a resistance to flow. And what happens is, because it heats up, it starts to glow and give off light at a specific temperature. And we're going to talk about what causes that. Why do materials give off light when they're heated? That's one of the reasons why we're going through this chapter. So for now, though, I want you to note that when we do this particular thing with this material, we get a continuous spectrum, right? Continuous spectrum. Now let's look at a few other things. What happens with other matter, not just tungsten, but other things when we heat them up to very high temperatures? What do we end up seeing? Is it the same situation always? Do we always get the same rainbow pattern, or do we see something different? So let's take a look at some of those other experiments. So what we're going to look at are the results of an experiment when you take something called a gas discharge tube and you heat them up to very high temperatures using a similar technique as when we heat up a light bulb. We basically, what we're going to do is we're going to look at, if you take a tube of glass, which are shown here, these are different glass tubes, and you evacuate the tube and then you pressurize it with a single type of gas. So we'll look at a few. These are just some examples of like when you do this with helium or neon or argon, krypton, or xenon. So these are all the noble gases. Now, if we take these noble gases in these tubes, or they're the only thing in there, and then we basically plug them into a voltage source, that voltage source heats the gas up to very high temperatures. And you'll notice that you get very distinctive colors from the different tubes, from the different gases in those tubes. Now, just like when we look at a regular light bulb, we are only seeing this color coming out of these gas discharge tubes. We see this color, but another question to ask is, well, what happens when you look at this light that is sort of coming out of these gas tubes? What happens when you look at that light through a prism, just like we did with the incandescent bulb? So that's actually what I want to show you next. So in this first picture, I have a gas discharge tube, just like the ones that you saw above. This gas discharge tube, however, contains nitrogen gas. So this is N2 gas that is in here, and you'll see it's glowing. It looks a little orange. Now, what you can't see sort of in the shadows here because it's dark is there is a fixture, a light fixture behind this, and it's black. And basically this is where this tube is mounted, just like you would a light bulb. So it's connected down here at the bottom and up here at the top, and then this whole box is like plugged into the wall. Okay, so there's it's electrically charged, so there's like a voltage going in this direction, and there's like electrons traveling up through this tube and into a filament that is down here, which heats up a lot, so kind of like a tungsten bulb would. Except it's not tungsten, so a different fixture down here, and then we heat this up to a very high temperature, and then the gas starts to glow, and we get this orange color. Now this is what we see with our naked eye. What do we see when we pass this light through a prism? Okay, so when you pass this light through a prism, notice that we get a rainbow-like pattern, right? So basically what you have here is the prism somewhere in between these two things, and the light traveling from the nitrogen gas that is excited by the electricity, and then the prism separates this light into the different wavelengths based on what's present. So what do you notice that's different about this spectrum compared with the spectrum that we get from the incandescent bulb? Well, notice that there are several colors missing, right? So for example, we don't see anything in here. There's a small gap in here, small gap in here, and some in there as well. And actually, if you looked at this very carefully, which people have done with like a microscope, you can actually see a very clear line pattern where there are distinct, totally absent gaps of colors that just simply aren't there, which you don't see in the incandescent light bulb. That's an interesting thing, like what's going on here. Let's see if this phenomenon occurs with some other materials as well. So down here I have a similar setup. However, in this tube, it's not nitrogen. This is a gas of hydrogen, a tube of hydrogen gas, I should say, that is in this tube. So same idea, this is hydrogen gas being heated up to very high temperatures, and what do we see when we put this light through a prism? Well, let's take a look over here. So we have the same setup going on where we have the hydrogen gas illuminating and the light traveling out, hitting a prism, and then traveling forward. And then we see the different wavelengths that are separated by the prism over here. So we see some red, we see a few different blue. So we also notice there's a very large gap of light in between. So this is a gap, okay? And this is very interesting. Like we see a lot of missing colors, and hydrogen, of course, we know is like the simplest of the elements, and we see a very simple spectrum. When we looked back at nitrogen is a lot more complicated than hydrogen. We saw a lot more bands of light. So we're going to think about this, like maybe it has something to do with the complexity of these things. But it's interesting to note at this point that you get almost a fingerprint for hydrogen that looks like this, and a completely different one for nitrogen. So it looks like it's a characteristic feature for elements. And actually, if we continue this and look at a few other samples, we notice the same pattern. So here in this blue light that I have here, this is actually a mercury lamp. So what we have is a vaporized mercury gas, and then that's being illuminated, passed through a prism over here, and then we see only blue, green, and then if you actually look in and zoom in a little closer, you see a few different greens. So that's very interesting. We don't see any orange or red going on there. And then if we continue this, we can do a few more elements. This is helium. So let's write that down, helium gas that's in here. And that is being excited also, and you'll notice that when it's passed through a prism, you get a lot of different colors, but it doesn't look like a rainbow, right? There's no real blue in there. We see the violet, and we see the red and the orange, but it's just not continuous. All of these are called discrete spectra rather than continuous spectra. We also call them line spectra. So all of these are examples of line spectra because we have lines of light rather than a continuous spectrum. And what we want to understand is, why is this happening? Where is the light coming from? What do the gaps mean? And basically what's going on with this. So to get at that, let's go to the next page. So let's just revisit what we just talked about. We see that if we have some kind of a hot gas, and we can heat this up with electricity, but this also happens in, like, for instance, a star. That hot gas, when it gets hot, it illuminates, so it sends out light. Right? So this light is traveling forward. And if we look at that light through a prism, we can separate out the different wavelengths. So we can get like wavelength 1, wavelength 2, wavelength 3. And depending on the gas, you get a different collection of wavelengths. So you can identify the gas that way. And this has actually currently is used to identify the makeup of different stars. So you can, if you go into astronomy, they do something called stellar spectroscopy, which is looking at the line spectra or the emission spectra for distant objects. And they basically can fingerprint the elements that are present in a particular star by looking at the spectra, because each element has its own particular line spectrum. So let's think about this a little more. Like, what do we need? What does this tell us about matter? That's what we're really trying to figure out. And what, in particular, what does it tell us about the structure of the atom? So to understand what's going on here, we want to remember that each of the lines that we see in the emission spectrum has a unique wavelength, right? We have different colors. Red is a lower wavelength than orange, and orange is a lower wavelength than blue. And so if we look at this one, for example, we have 6 different wavelengths. And because we have 6 different wavelengths, we also have 6 different energies. Each of these lines on the spectrum represents a different energy of light. So why are we getting these different lines? Where are they coming from? Why are they the colors that they are? And what are these black spaces in between them? Let's try to understand that. So to do this, let's think about a simplified model of the atom where we have just the nucleus in the middle and then an electron on the outside. And I'm going to make a nucleus a little black circle, and then we'll use an electron as a green dot. And over here I have the nucleus and the electron outside of the nucleus. Now we know that the electron is outside of the nucleus and it's orbiting around, so it's kind of moving around. Now, what else do we want to know about this? Well, let's say that this electron, this gas that this electron is a part of, let's say that this increased in energy. What happens to it? Well, when this gas is heated, this atom is heated, the electron goes from this energy state to a higher energy state, which looks like this. It's farther away from the nucleus, okay? And once this is called excited state for the electron, when it's up there for some period of time, it eventually is going to go back down to its lower energy state. Okay, that's the lower energy state. So we have these 2 states. If I stop moving around there, we have this like lower energy state, and then when it's farther away, it's at a higher energy like that. Okay, so let's break this down into a few stages. Now, I'm going to call this original one here, this is called the ground state. Now, if I heat this thing up, so if I put some energy into this thing, this is like heat. And I can do that by applying a voltage to a filament so that it causes that gas to heat up. What's going to happen is that electron is going to go from this ground state, it's going to increase its potential energy, and it's going to move farther away from the nucleus as it's orbiting. Okay, that's called absorption, okay? So it's up here in this higher energy state. So what happens now is that it's going to have to eventually go back down to its lower energy state. So let's just write this down real quick. Say this is the higher potential energy, right? Because it's farther away from the nucleus. And I'm going to put a little, like a platform right there where it can be at. So it's at a higher potential energy. And let's say that at the ground state, the original state it was in, is down here. This is a lower potential energy. Now, we got into this higher potential energy when we heated up the gas, right? What's going to happen after it starts to cool down? Well, what's going to happen is that electron is going to move from the higher potential energy state to the lower potential energy state. And when this electron falls back down from the higher potential energy to the lower potential energy state, it has to give off energy. And it does that in the form of a photon. And this photon that is released, in terms of its kinetic energy, is exactly equal to the difference in energy between the higher potential energy state and the lower potential energy state. And that's why we get the different wavelengths of light. Each wavelength is the result of an electron transitioning from a higher state to a lower state and producing a photon with a particular energy. So we might be able to say that these lines tell us what energy states electrons outside of a nucleus can exist at. they can exist at the energy state that correlates with, say, the wavelength 6 or with wavelength 1, or any of the others that are shown. Now, what about these black gaps in between those wavelengths? If the bands of light that we see represent allowed energy states for the electron, what do the black gaps represent? Do they represent places where the electron will have an energy? No, they represent places where the electron cannot be. Okay, these gaps between the bands are energy states that the electron simply doesn't exist at. Now, in the early 1900s, when all of this was first discovered, scientists had a relatively difficult time explaining all of this using the theories that were available at the time. And here's why. Basically, the existing theory, before the modern theory that we're getting into now was developed, the existing theory went something like this. So first off, if we imagine the electron existing in the space outside the nucleus, this electron should be able to be pretty much anywhere outside of it. And if it's anywhere outside of it, when it goes up in potential energy, it can absorb any amount of any energy to do that. And then when it goes back down and relaxes to the lower energy state, it will emit all of that energy. And we would not expect to see a line spectrum, but we would expect to see a continuous spectrum if that electron, that green dot, can exist at any energy outside of the nucleus. Okay, so let's look at this question that's presented here. Is the line spectra observed when heating a gas are not explained in terms of this logic that's up here. So why not? Well, if we look at the line spectra, we see those bands with certain colors, and we discussed that those bands represent certain energy levels. And the fact that we have an absence of many colors, say, from hydrogen, for example, we're missing a lot of colors, that tells us that that electron around hydrogen can't exist at those energy levels. So really, it's that the line spectra show us that the electron can only exist at certain specific energy levels. And those specific energy levels will vary depending on the type of atom we're talking about, or the atom we're looking at. Okay, and there's a reason for that. It's every atom has a different number of protons and a different number of electrons. So of course the energy levels change depending on what atom it is. We also say that the electrons, because of this, are in what we call a quantized. They're quantized. They're in a quantized environment, or they're in a quantized state. What that means is that the electrons don't have an infinite number of options to choose from when we're talking about their energies. They only have certain options to choose from. It's a lot like a staircase, actually. And I wanted to show you this model. Actually, somebody I was looking at online had made a model of the energy levels using sort of a Lego piece. And this kind of represents the situation that we're talking about, where this Lego piece down here is an electron, or represents an electron. And these are the different energy levels here. So we have like energy 1, energy 2, energy 3, energy 4, etc. Now notice that there's no, this little piece, we can put it here, or any of the other steps, but it cannot exist anywhere in here. This is the situation that the electron is in. It can exist at any of these energy states that are available to it. And of course, the placement of those will depend on what atom we're talking about. But there is nothing in between those states. This is called quantized. And a lot of actually all the subatomic particles, because they're so small, it turns out, have this quantized behavior. And the physics of this quantized behavior is called quantum mechanics. The mechanics, or the physics, of these subatomic or very small things that have quantized states where there's only discrete energy levels available. Let's look at this next question here. It says, if the wavelengths of light represent energies that the electron passed through as it went from a higher energy state to a lower energy state, what do the missing bands of color tell us? Well, the missing bands of color tell us simply that the electron cannot exist at those energy states. So in that particular matter, those energy states that are missing are not available for the electron. So the electron can transition between the energy states that are available to it, but they don't exist at any of them in between. So if we draw a hypothetical chart of some energies, like energy 1, energy 2, and so on, it's fine for the electron to be at energy 1 or energy 2 or energy 3, but not like energy 1.5 or something in between, or 2.5. So we can't have those transitions. Those aren't available, and thus we don't see those colors on the spectrum. Okay, so now that we have a general idea of where the bands are coming from in the line spectrum, from the electronic transitions, I want to show you a few more just visual graphics just to kind of drive the point home. So before we go to the next page in the notes, I'm going to go to one more screen to show you some visual aids. So let's take a look at those. So I'm showing you here what's called the Bohr model of the atom, which we're gonna go over on the next page in the notes. And this is what we've been talking about so far. It's a more modern picture of the structure of an atom and where the electrons are. So Bohr was a scientist back in the early 1900s, sort of a contemporary with Einstein, and he recognized that the line spectra that we were just looking at showed the electron could only exist in quantized or discrete energy levels outside of the nucleus. And this is his model of the atom, is that we have over here these n is equal to 1, n is equal to 2, and so on. These represent discrete, what he called orbitals outside of the nucleus. And he imagined the electron simply just traveling around in an orbit somewhat like a planet going around. Now, this is an incorrect idea because it doesn't make physical sense, but you can imagine it that way right now, is that an electron in this n is equal to 1 or low energy state close to the nucleus is here. And if it's in another energy state, a higher energy state, it's farther away from the nucleus, say in n is equal to 2. So that would be up here. N is equal to 3 is here, and n is equal to 4 is here. Now, as we increase this letter n, so n is equal to 1, 2, 3, 4, we are increasing the potential energy of that electron. It's farther away from the nucleus and has a higher potential energy. So the higher this n is equal number goes, this is called the principal quantum number, n. The higher that principal quantum number, the higher the energy level. Now, it's interesting in that really what Bohr was saying was that the electron can exist here or here or here or here, but it doesn't go from here, this energy level, n is equal to 1, to n is equal to 2, through a transition between the two. There's no in-between energy for n is equal to 1 as n is equal to 2. It goes directly from this energy to this energy instantaneously, like this red dot is doing. It's not going like this, and then like this, and like this. So it's not like if we imagined it orbiting like this, it's not going like this. But in fact, it's orbiting. And then if the energy is increased, it immediately is over here. Okay, that's the quantized nature of the electron. Now, using the Bohr model of the atom, it is easier to explain what happens when we see the line spectra, the emission spectra for an atom. Over here on the left, I have an atom in what's called the ground state, where the electron is in the lowest available energy state around that atom. So n is equal to 1. We call this the ground state. Now, when we're heating the gas, the element, okay, what's going on is that electron is promoted to a higher potential energy state, say n is equal to 2. It might go to 3 or it might go to 4, but it goes higher in energy nonetheless. And that, of course, what energy level it goes to depends on how much energy it absorbed. And it turns out for it to go to n is equal to 2, it needs to absorb exactly the amount of energy that is available the gap between the energy of n is equal to 1 and n is equal to 2. And if it absorbs that delta E, we'll call that delta E1, the electron can be promoted to that second energy level. But if it absorbs a different amount of energy, say we'll call this delta E2, it would go to n is equal to 3 instead, and so on. So that's this process of the electron being promoted from a lower potential state to a higher potential energy state. This is called absorption. And don't worry, I'm going to summarize all this on the lecture note page that we have next. So let's then look at where the actual line spectra, the light that we see, actually comes from. So I've simplified it a little bit, actually what colors belong to what transitions here, but just for illustrative purposes. So you can kind of understand what you're seeing and why you're seeing it. So every time an electron is promoted to a higher energy state, say an electron is at the n is equal to 2 state, that high energy state does not last forever. Just like if you throw a ball up into the air, it will eventually fall to the ground. It's because it will fall to a lower potential energy state. And that's exactly what the electron will do. The electron will transition from n is equal to 2 to n is equal to 1. And when it does that, a photon of light is emitted that is equal to the gap in energy between n is equal to 1 and n is equal to 2. So this gap, notice this gap is the smallest gap here. That would be the lowest energy transition, and therefore we get the lowest wavelength of light, or red. Now, what if the electron was at a higher energy state, say n is equal to 4? That's the highest potential I have on this diagram. And because of that, the gap between n is equal to 4 and n is equal to 1 is much greater. This is like if we dropped a ball from, say, the top of a skyscraper. When it hits the ground, it releases a lot of kinetic energy. And just like that, the electron, when it falls this far, emits a photon of very high energy, in this case, violet. If it was higher in energy, say up here, it might emit ultraviolet. And if it was lower in energy, say if there was another energy down here, it might emit infrared. So these wavelengths of light are directly equal to the difference in energy between the allowed energy states for the electron. And that's why we get the line spectra. Now notice that we don't have any lines on this diagram. Again, this is hydrogen actually. We don't have any energy gap in here. So like there's nothing here. That's because there's no energy level at this state. It just doesn't exist. Okay, so that's the origin of this, and that's why that we have the black lines. Now, let's summarize all this on the next page in the lecture notes and write all of it down. So let's go take a look at that. So this is the Bohr model of the atom that we have started to develop looking at the line spectra, the emission spectra for different elements, and recognizing what that means as far as where the electron is in terms of its energy. And we've learned about these discrete or quantized energy levels for the electron. So let's write some of this down. The first thing we want to note are some of the terms that we use to describe the energy levels. So because the energy levels are quantized, and this falls under the domain of what later became, after this was discovered, quantum mechanics, the energy levels are located at an integer number. So n is equal to 1, n is equal to 2, and so on. And we call these integer numbers the principal quantum number. And the higher the principal quantum number, the higher the potential energy for the electron. Now, instead of drawing the energy level as sort of circles around an atom, we usually make it a little more concise by drawing them qualitatively as lines, kind of like platforms outside of the nucleus. So we show them as, they're called Bohr energy levels, like I'm showing here in this diagram, where the one at the bottom is at the lowest energy level. And you can imagine the nucleus being somewhere like below this. And the n is equal to 1 is at the lowest energy level. And n is equal to 2 is a little bit higher than that, and so on. Now you'll notice that the energy levels, the spacing between them decreases as you increase the principal quantum number. Now you might ask the question, how do we know that? Well, actually that comes from, again, from the experimental observation of the line spectra themselves. So when you look at the line spectra, the emission spectra for different elements, and you also look at different temperatures at which those elements are heated to, you will start to notice this observation. So as an example, for tungsten, that we saw in the incandescent filament, when we saw that continuous spectrum where we didn't see the separations between the lines, we just saw most of the colors. That happens because we are heating the tungsten up to a very high temperature, and thus the electrons around it are in a very high energy state. So what happens is the spacing between the transitions decreases as you go up in energy, and therefore we see very small differences between those transitions when we look at the emission spectra. Now, this is usually how we depict in a qualitative way the electrons outside of the nucleus. And we're going to be looking at this quite a bit as we move forward and figuring out what the electrons are doing when they're in a particular energy state, or when they're in n is equal to 1 or n is equal to 2. We'll see that they have different sort of substates available to them. And so while we have this now we have this picture of sort of the energy states that are available, let's say, to an electron, we also are going to need to show where the electrons are. And instead of using dots, we will use dots later for other things. We're actually going to use, when we drew these Bohr energy levels, we are going to use arrows. And we're going to use arrows that are, I'm going to change colors actually. I'm going to use green arrows right now, or red, I guess. We're going to use up arrows and down arrows. And you're going to learn why we use up arrows and down arrows later, but we're going to use these to represent electrons. Okay, and they are representing what it's called the spin state of the electron. So this we'll call this a spin up electron, and we'll call this a spin down electron. And we're going to learn what that means later on. But an electron can be spin up or spin down, and then it can be in a particular energy level. And we're going to show that by drawing the arrows on the energy levels. Okay, so we might have like an electron here, and maybe it's with another one here. Okay, so we're going to show them, we're going to treat those energy levels like platforms for the electrons. And when we draw an electron on one of those platforms, it represents an electron in that state. So these electrons, these are electrons in the n is equal to 2 quantum state. So we'll just call it the state. Okay, they're in the n is equal to 2 state. So we also learned how the Bohr model explains the energy changes going on with electrons when they're excited, when the electron absorbs energy, and when they relax to a lower energy state, and how they emit photons. So to explain this, I'm going to draw a little diagram of the Bohr energy levels when we see the change between the ground state and the excited state. So over here I've drawn the ground state where the electron is in the lowest available energy, or n is equal to 1. Now, when this atom is in the lowest energy state, and let's say a photon impinges on that electron, it excites that electron to a higher energy level. So it goes from the ground state to a higher energy level. So say from n is equal to 1 to n is equal to 3. Now, the energy level that it goes to obviously will depend on the energy of the photon that hit it. So if the photon that I just showed there was in energy equal to the difference between n is equal to 1 to n is equal to 3, we could excite that electron to n is equal to 3. But if it was only, say, the E on it, the energy of that photon was only the difference between 1 and 2, it would go to the 2 state. And we can use that information, we can sort of measure how much energy is absorbed or emitted to figure out, to actually deduce what the actual energy levels are around in an atom for an electron. So that's the ground state and the excited state. Now, of course, there's also the emission part where the light actually comes from. Right? So this electron that's up here in this higher energy state will eventually have to fall back down to a lower energy level. And when it does that, it will also emit a photon that tells us the energy level of that transition that it went through. Okay, so that's pretty much the Bohr model. Let's go to the next page. So let's wrap up today's lesson with this page. We're in part B of the first part here of this lecture note outline. So we're talking about absorption and emission, and let's just kind of summarize, where does the line spectrum originate from? Basically, it originates from when we take a gas and we heat it up somehow. Energy is absorbed by the electron in that gas, and that electron is promoted to a higher energy state, or n is greater than 1. This process is called absorption. Now, this excited electron won't stay in that high or that excited energy state forever. It will eventually relax from its excited state back down to the ground state. And when that happens, energy must be given off because we're going between two different potential energies. So there's an energy transition that's occurring. And when that happens, the particle, that charged particle, the electron, that represents the electron sort of accelerating or decelerating in an electromagnetic field. And that causes a photon to be released. This is called electromagnetic radiation. And we specifically, this process is referred to as emission, or the emission of a photon. So the last point here is, why then do we only see discrete or line spectra rather than a continuous rainbow? And to answer that, we have to remember or recognize that this experiment tells us that the electrons can only exist at certain discrete energy levels. And for that reason, we say that the electron is quantized. Its energy is quantized. So I'm going to write here, it's because the energies of the electrons are quantized, meaning only certain specific or allowed energy levels are possible for the electron, and that's why we only observe those transitions. So that's pretty much it for today's lesson. Next time, what we're going to talk about is a little more about the electron, and we're going to get some more details about what these different energy levels mean in terms of, for our purposes, what they mean as far as bonding goes. And we're going to look at something called the orbitals. We're going to look at the shape of the orbitals when we have an electron at different energy levels. So we're going to talk a little bit about the wave nature of electrons and the shapes that they take on when they are in these different energy levels. So let's stop there. I hope you're doing well. Let me know if you have any questions. See you soon.